Stripping down science. The Naked Scientists.
Hello, well, welcome to this week's Naked Scientists. I'm Chris Smith, and I'm joined this week by Kat Arney. Hi, Kat.
Hello.
Now, coming up shortly, how scientists have got to the root of hair replacement. So that's good news for anyone that's going a bit thin on top, but bad news if you make wigs for a living. Also, a new, much safer way to make hydrogen to power our clean cars in the future. A virus that's been programmed to kill cancers, and why a dose of herpes could actually be good for you. Sounds nasty.
I still don't believe that one. Also this week, we're focusing on the science of the atmosphere. We're going to be catching up with Aberystwyth University's John Grattan to hear about the worst atmospheric pollution event in history, which I reckon was Chris farting or something like that. What was it really? Keep listening to find out. We'll also be talking with Jonathan Shanklin from the British Antarctic Survey, and he was one of the team of scientists who discovered the hole in the ozone layer back in the 1980s. So he's going to be chatting a bit about what the ozone layer is, how it protects our planet, and whether it's still there. You know, is the hole still there? Is the ozone there? Plus, we've got Cambridge University's Rod Jones, who's going to be explaining to us why water is actually a more powerful greenhouse gas than carbon dioxide. And if you want to have a go getting in on the act with the atmosphere, you can join in our kitchen science. What you'll need is a 2-litre plastic bottle, some water and a match, and you can make your very own weather system.
And it's really cool. I can testify to that because I've actually seen it happening, and I've just chatted to the guys and they're ready to go at King Edward VI Grammar School, and it is an awesome experiment. So go and grab a bottle, 2-litre bottle of something. You don't need the fluid that's inside. A little drop of water and a match, and we'll be telling you how to do that shortly. Now, if you're in the mood to win something, we've got 2 great prizes up for grabs this week. We've got a copy of a new book which has been published by Gabrielle Walker. She writes for New Scientist magazine, and it's called An Ocean of Air, and it's all about how the atmosphere works. Plus, there's a signed copy of my book, which is Naked Science, and that takes a look at some of the fun and funkier scientific discoveries of recent years. Now, if you want to win a copy of those 2 books, we've got a suitably atmospheric question for you this week. What we want to know is, what percentage of the air at the top of Mount Everest is oxygen? What percentage of the air at the top of Mount Everest is oxygen? And the person with the closest answer is going to win.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, that teaser question was actually inspired by a pretty amazing feat this week, Kat. I don't know if you read pretty much every newswire carried this. An English guy was the first person ever to paraglide over the top of Mount Everest.
This is Mr. Bear.
Yeah, Bear Grylls. It sounds like something you get in Yellowstone, actually, doesn't it? But in fact, he's an ex-SAS man. At the age of 23, he was also the youngest person to make it to the top of Mount Everest and come back alive. And so, at the age of 32, decided the ultimate feat, let's paraglide to the top of the world's tallest mountain. So, together with a teammate who's designed a special engine that's capable of tolerating very low oxygen conditions, he strapped this engine on his back, fixed to a big propeller, and drove his paraglider, together with this other guy, to 29,000 feet, which is the height of Mount Everest. Unfortunately, his teammate, this other guy who designed the engine that got them there, his engine conked out at 28,000 feet, so 300 yards short of the top. He had to return home, but good old Bear made it over the top. And he said it was a pretty awe-inspiring experience, and also one of the most frightening things he's ever done. Now, this guy used to be in the SAS, and for him to say it was scary, but to look down on the mountain that he got to the top of about 9 years before, pretty amazing. He has said now, though, I have a daughter, I have a wife, and therefore I have a bit of a conscience. I've used up more than my fair share of my 9 lives, so I'm going to keep 2 feet firmly on the ground. But his wife says, I don't believe it.
It'll just be going to the shops and, having a quiet life from now on.
Now, into the science news now. And a very interesting discovery, and talking about atmospheric science and pollution and that kind of thing, very interesting stories come out of Purdue University this week. It's a guy called Jerry Woodall, who works on chemistry, and he was mixing up some gallium, which is something that you usually use to make semiconductors, LEDs, and some aluminium. And he made this mixture, melted the 2 together, and later on was cleaning out the crucible that he'd done it with, and poured some water into it, and there was this sort of poof, and a bit of a mini explosion. And he thought, well, what the hell was that? And they worked out what was going on and then realised this could be the key to making hydrogen on demand in large amounts. Now, why is this important? Well, if we want clean fuel for vehicles in future, people think hydrogen, good idea, because hydrogen, when you react it with oxygen in the air, it just makes water, H2O. So it's the only thing that comes out of your exhaust pipe would quite literally be steam. So that sounds like the ideal fuel. So how do we make enough hydrogen to pull this one off? Because no one wants to drive around with a cylinder of hydrogen in the back of their car. I mean, the Hindenburg showed that was a pretty bad idea. So we want something that when you react it with something else that's safe, gives you large amounts of hydrogen on demand to put into your engine. Well, when they looked at the chemistry of what was going on with this aluminium and gallium mix, they found that normally aluminium won't react with water because the metal gets a skin or a surface layer of aluminium oxide that stops the water getting in contact with the metal, and it stops it making any hydrogen. If you mix it with this gallium, this rare earth material, then what happens is it prevents the aluminium forming this oxide film, and this means that all of the aluminium continuously remains active and in contact with water, so it can produce huge amounts of hydrogen just by adding a little bit of water. So they've produced some pellets, which are these gallium aluminium pellets, and if you add water, you get large amounts of hydrogen off, and the aluminium turns into aluminium oxide, alumina. And you can recycle that just by electrolyzing it. So they're saying this could be a very clean way to power cars in future, because you could take the pellets, because the gallium doesn't get used up, it just remains behind as a sort of catalyst. You could take these pellets, get the aluminium oxide out, electrolyze it with power from, say, a wind farm, say hydroelectric energy, or even nuclear power, so it's carbon neutral, and regenerate the aluminium again. Hence, more fuel. Is it going to be expensive? Well, he reckons that the average family car with an aluminium gallium tank of these pellets they've made could make a 350-mile round trip, and it would cost about $60, which, on par with what Gordon Brown's got in mind for fuel prices here in the UK, that sounds like good value.
That's pretty good going. Where do I get some? I love the way, as well, it was just serendipity that led to that. Cleaning up something, it explodes. It's a new form of hydrogen. Brilliant. Anyway, on a more serious note, this week, Cancer Research UK funded scientists at the Institute of Cancer Research in Surrey have been testing a new way to kill bowel cancer cells with a kind of a smart bomb. And the technology is called GDEPT, which stands for Gene-Directed Enzyme Prodrug Therapy.
It's catchy.
It is certainly catchy. It's based on a rather clever virus and a harmless chemical that goes by the incredibly catchy name ZD2767P, which is a kind of chemical called a prodrug. Now, the scientists, who are led by Professor Caroline Springer, have engineered a harmless cold virus, an adenovirus, to contain an enzyme called carboxypeptidase G2. And the enzyme's only activated when the virus infects cancer cells, because it's designed to respond to telomerase, and this is a protein that makes around 8 out of 10 cancers basically immortal. So, the virus infects cancer cells, and because they have telomerase, it switches the enzyme on, but it doesn't switch it on in healthy cells because they don't have significant amounts of telomerase.
How do you get the virus into the cancer in the first place?
Well, you can just infect someone with these viruses. You can either inject them near the tumour or systemically infect someone, because it won't significantly, even if it does infect healthy cells, it doesn't matter. It's
not a major problem that the vast majority of the population have had adenoviruses, i.e. colds, in the past, and therefore they might have antibodies that might stop it working.
Well, they're engineered viruses for a start, and obviously this isn't something that's going into clinical trials tomorrow. But the really clever part of this, so you have the virus in cancer cells, and it's switched on, and it's making this enzyme. And then you give the cells this prodrug chemical, and the enzyme converts it to a cell-killing chemical. And so therefore you've got something that cancer cells are basically making their own suicide bombs. And they tested it in bowel cancer cells that they'd grown in the lab, and then they tested it in mice with bowel tumours. And they found that actually this technique could double survival in mice that had been treated. So it could potentially be quite a useful way to treat cancer, because it's really specifically targeted to cancer cells.
Because a major problem with anti-cancer therapies is very often you end up harming the body as well as trying to kill the cancer, and you get side effects.
Exactly, and sometimes it's a bit of a race to see, can you kill the cancer before you kill the patient? But, the new generation of cancer therapies are much more targeted, sort of virus therapies, smart drugs, so hopefully we're going to really start seeing the revolution soon.
Well, that's good news. Let's hope that it does actually pay off in the long run. We're sticking with the sort of virus theme, Kat. There's a very interesting story that's come out of Washington University in St. Louis, Illinois this week. Skip Virgin is the name of the researcher. He's a herpes virologist. And what he's published in this week's edition of the journal Nature is this very interesting finding that if you take the rodent or mouse equivalent of some of the common human herpes viruses, including the glandular fever virus and also cytomegalovirus, which causes another glandular fever-like illness, these are both herpes viruses, so a bit similar to chickenpox and cold sores and genital herpes. If you infect mice with them, let the mice get over the acute infection, and then you challenge them with infection with the plague, Yersinia pestis, and also listeria, which is another bug which people have heard about because you get it from soft cheese. You also get it, if you're elderly, you can get, say, a meningitis caused by it. It can be nasty. And the animals that were challenged with these really quite pathogenic bacteria all survived, where previously they didn't. So this virus is in some way, by infecting the body, tuning up the immune system and making it stronger. And what they've done is to track it down to 2 immune-boosting chemicals. One of them's called interferon gamma. Another one's called TNF-alpha. And so when the virus goes into the body and establishes this lifelong infection, because herpes is with you for life once you're infected with it, it secretes these factors which tweak the immune system, make it stronger, and help you to fight off bacteria. Now, why should this happen? Well, herpes wants to live in you for your entire life. So it's got a vested interest in wanting to keep you healthier, because if you die, the virus's host dies, so the virus has got no home, it would die. So it's got an interest in wanting to keep you alive. And what Skip Virgin reckons is that because these viruses are ancient as the hills, they've been around for millions of years, that we have sort of developed not so much a parasitic relationship with them, they're parasitising us. It's more like a symbiotic relationship where that we give the virus a home, it gives us a stronger immune system.
So in your medical opinion, though, should we be trying to catch herpes to avoid the plague?
Well, you could say that, in fact, people already do that because 90% of the population are already infected with a large number of herpes viruses. Most of us have had chickenpox. Most people have had herpes simplex type 1. That's the cold sore virus. Most people have had Epstein-Barr virus, which is the one they tested in this, that causes glandular fever. So, in fact, we're probably already, as humans, benefiting from this amazing discovery of what these herpes viruses can do for us.
Let's hope we don't have to test it in a plague outbreak. Anyway, completely different. I'm going to try my hand at physics now, which I'm not usually very good at. But physicists at the University of Pittsburgh have created an entirely new form of matter, and they published their results in the journal Science this week. Now, unfortunately, it's not actually a form of chocolate with no calories in. I'm still waiting for that one. But the new matter is called a polariton superfluid, and it combines the characteristics of laser light with the world's best electrical superconductors. Now, to create this new type of matter, the scientists basically filled a little nanoparticle cage with tiny energy particles called polaritons. And because you've trapped them in this tiny cage, it slows them down. And this means they actually come together and start to act in a coordinated way as a single energy wave, rather than like a load of particles just bouncing about all over the place. Now, this wave, and as we know that light is a wave and a particle, the wave produces light similar to laser light, but actually using a lot less energy. And the researchers also found that the energy could move around from point to point within the superfluid. And this is similar to the situation you get in superconductors, which are really highly efficient electrical conductors.
So how are we going to use it?
Well, there's 2 points to this. Now, normally, experiments like this have to be done at really, really low temperatures. So we're talking like minus hundreds of degrees, because superfluids and superconductors are very unstable. But this new polariton superfluid seems to be much more stable. And in fact, the lead scientist, Professor David Snoke, thinks that he could probably even do it at room temperature. Now, it's still quite esoteric physics at the moment, but in the future you could transfer light through solid matter, you could move energy around, so this could be really useful for building super fast computers or for communication technologies.
We made light of that one. Thanks, Kat. It's The Naked Scientists with Dr. Chris and Dr. Kat. Don't forget, this week we're talking about the science of the atmosphere. We'll be finding out from Aberystwyth University's John Grattan about what was the worst atmospheric pollution event in history. Have you any clues what that could be? We'll find out from him coming up very shortly. Also, we'll be hearing from the British Antarctic Survey's Jonathan Shanklin, who is one of the team who discovered the hole in the ozone layer in the mid-1980s. But what is the chemistry of ozone? How does it protect the Earth? And has that ozone hole got worse, got smaller? Are the mechanisms we've put in place to try and tackle the problem actually working? That's all on the way. If you want to have a go at having a chance to win a wonderful book we've got from Gabriel Walker from New Scientist magazine, it's called An Ocean of Air. That's the new book. It's all about how the atmosphere actually works. There's also a copy of Naked Science, my book. We've got an atmospheric teaser for you this week. What we want to know is what percentage of the air at the top of Mount Everest is oxygen, and the person with the closest answer is going to win.
The Naked Scientists, supported by the Wellcome Trust.
In other news now, and some good news for the follicularly challenged, it turns out, because researchers at the University of Pennsylvania have taken the first steps towards a cure for baldness. They noticed that when wounded skin was healing, some of the cells in the upper layer of the skin, called the epidermis, turned into hair follicles. And by looking at the genes that were turned on in those cells, they were able to isolate a particular genetic pathway that lets hair follicles form during healing in the same way as they did during embryonic development. Professor George Kotsourelis told me how it works.
The dogma has been that hair follicles do not develop during adulthood. So once you lose a hair follicle, the prevailing wisdom has been that you cannot regenerate it. So we were surprised to find that actually when we wounded mice during the healing process, we noticed new hair follicles forming in the center of the wound. And on close examination, we realized that these follicles were undergoing very similar changes that are found when the hair follicle first develops in the embryo.
Now, when you say you wounded the skin, do you mean you actually removed a full thickness piece of skin or just the surface? What did you take away?
We actually removed the entire skin at full thickness on the back of the mouse and allowed it to heal.
So if you made a full thickness injury to the skin, that means that the regeneration of those hair follicles, the cells that are doing that, must be coming from somewhere else. It's not some deep-rooted stem cell coming in from below the lesion. So where are those cells coming from?
We were first expecting to find new hair follicles to be coming from the stem cells that are actually present in the hair follicles at the periphery of the wound. But we were quite surprised to find that although the stem cells at the periphery of the wound contributed to wound healing, these cells did not contribute to the new hair follicles. What we actually found was that the hair follicles developed from cells in the epidermis and from the upper part of the follicle.
So what sort of cells are they then? If they're not follicle cells, what's actually producing the follicles?
The epidermal cells that are creating these follicles are essentially reprogrammed and instructed to make a new hair follicle. So the signals that go between the epidermis and the dermis during the neonatal time period or during embryogenesis are reutilized in the adult to regenerate new hair follicles in the face of wounding.
Do you know what the factors are which are provoking those stem cells which are in the skin? Because presumably that might be quite an interesting pattern of genes to know about if we want to try and recreate hair follicles in aged men.
We know from developmental biologists who've been working on hair follicle development that the gene beta-catenin, which is in the Wnt pathway, is very important for normal hair follicle development. So we looked at beta-catenin, and it was being expressed in these new follicles. And we also then blocked beta-catenin after the wound had closed. If you block beta-catenin at that point, then no new hair follicles will form. But perhaps more exciting than that, when we activated the Wnt pathway, we found an increase in the number of new hair follicles that formed. In fact, the number doubled. So this indicates that during this wound healing process, the cells are susceptible to manipulation by signals that are known to be important for hair follicle development. So we think that in the future we'll be able to design treatments based around the response that we see after wounding.
So there's hope for me yet then. That was George Kotsourelis from the University of Pennsylvania describing how he's uncovered the genetic workings of the recreation of hair follicles. So bad news for wig makers, good news for those of us that are destined to grow old and get bald. Well, time now to go stateside and catch up across the Atlantic with the team from Science Update. And Chelsea's going to be looking at how pollution affects rainfall, while Bob will be staring into the eye of a hurricane.
This week for The Naked Scientists, we're going to focus on the water in our atmosphere. I'm going to talk about how scientists are improving their ability to predict hurricane intensity. But first, Chelsea's here to tell us why some mountaintops may not be getting their share of H2O.
Air pollution from cities can deprive nearby hills and mountains of rainfall. This according to meteorologist Daniel Rosenfeld of Hebrew University in Jerusalem. Looking at 50 years of data from a mountaintop in China, he and his colleagues found that while air pollution has steadily increased, rainfall has decreased.
Not only that, but when we look at the day-to-day variability in the amount of rain over the mountain, it is going together with the day-to-day variability in pollution.
Normally, moist air deflects up a mountainside, then cools and condenses into rain over the mountaintop. But if that moisture condenses on air pollutants, the drops don't get big enough to fall. Rosenfeld says this effect could dry up alpine watersheds, causing problems for the very cities creating the pollution.
Thanks, Chelsea. And while hills and mountains may have the problem of too little rain, some coastal areas have had the problem of too much in the form of hurricanes. In recent decades, scientists have become much better at predicting the paths of hurricanes, but not at predicting sudden changes in their intensity. That's why University of Washington atmospheric scientist Robert Howes and his colleagues are studying a part of the hurricane called the eye wall, the strong winds around the calm eye of the storm. Howes says those winds gain momentum as the eye wall contracts, but eventually the eye wall collapses and is replaced by a new one that's wider and weaker.
And this has a great deal to do with the intensity of the storm as a whole. The wider the eye wall, usually the less intense the winds.
Using data from planes flown into the eyes of hurricanes, his team is learning more about the eye wall cycle. The data will help create better models for predicting a storm's dramatic fluctuations.
Thanks, Bob. Next time we'll talk about what scientists are learning about disorders of the brain, including Alzheimer's, depression, and schizophrenia. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys, and there'll be more from Bob and Chelsea next week.
Sorting out the sparks from the quarks. The Naked Scientists.
And waiting in the wings, we'll be talking with John Grattan from the University of Aberystwyth about the worst atmospheric pollution event that ever took place in the history of mankind. What was that? We'll also be hearing from Jonathan Shanklin from the British Antarctic Survey about the science of ozone, and Professor Rod Jones from Cambridge University will be explaining to us about a gas that's far worse for global warming than carbon dioxide, and would you believe it's just humble water? And Dave's in Norfolk. Hello, Dave.
Hi, Chris.
Fire away.
Right, a question I did ask you a while back, right, but something sort of put me off it a bit, about drinking rainwater. Yeah, you said it was that was the best water there is. Yeah.
Well, it depends. I'd say measured, assuming that it's come through clean air in clean clouds. Then yes.
Yeah, because when you go out to your car after it's been raining in the morning, you get all dirt all over your car, like it's been raining and dirt, don't you?
You can do.
I prefer to drink rainwater if I could, right? But would it be better to put it through a filter or something, or is it safe to just drink it?
It depends where you are. Now, the interesting thing is that everyone assumes that clouds are sterile, but scientists in recent years have discovered that clouds actually contain lots of bacteria, and there are bacteria of a species called Pseudomonas, which is actually living in the air and gets up into clouds and might use clouds as a way of ferrying it about. And the reason the bacterium is able to do that is because it's invented a way of doing what's called ice nucleation. It's got certain chemicals on its surface that make tiny ice crystals form, and this makes the cloud form ice crystals around the bacterium, which makes it heavier, makes it flutter down to Earth, and so it can use the clouds and winds as a way of disseminating itself around the surface of the Earth. Those things, as they stand, though, don't harm you, but what can harm you is other chemicals that can dissolve in the water as the rain comes down to Earth, because the thing is that if you're in the middle of nowhere and there's no pollution sources around, the air that you're getting has come off of a pristine ocean and it's just landed at the foot of a cliff and you're drinking it as it comes down, that's probably pretty clean, Dave. But if you're in a polluted area, you're downwind of, say, heavy industry, power stations, those things could be pumping out a whole host of things, including different particulates, cancer-causing agents, dioxins, for example, and heavy metals even, especially if they burn car tyres, which lots of incinerators are now doing, including cement-making factories as well. Then that could all get into the water that gets rained down, because those particles get into clouds and they encourage the clouds to form water, and that forms raindrops and comes down on you. So I think if you said I was going to drink pristine rainwater from the Amazon rainforest, you'd probably be okay. But if you live downwind of industry, which, let's face it, in the developed Western world, you probably have a hard time finding somewhere where you weren't doing that, I think it's risky.
Yeah, when I was a kid, I used to drink out of the ground.
Well, I mean, where does our water come from? It comes out of reservoirs, it comes out of boreholes in some cases, so it does come out of the ground, but
the place
it's been chlorinated.
The place where I used to drink it is now a landfill site.
And then some would say that if you drink Thames water, then the quality of that water would have improved if it had become a landfill. But anyway, do you want to have a go at the quiz, Dave?
Can I just ask you the other question?
Oh, go on then.
Just a quick one. The lime scale in the kettle, right? Has it got any use? Is it useful for anything at all?
I reckon, because it's basically calcium carbonate, if I'm right, so you could collect it all together and make chalks.
Well, it's actually quite good for your health in the sense that we need calcium in our diet. The fact that it's in the kettle says that's been removed from the water that you're going to drink in your cup of tea. But if you were to just drink the water that it came from, you get that calcium into your body, and calcium's good for building strong bones and teeth. So calcium does have a role.
Right,
It is useful.
Okay, I'll have a quick go at the quiz then. Thanks.
Okie dokie. There are about 5 million red blood cells in the average human. Is that science fact or science fiction?
I'd say it's more than that. So, fiction.
Well done. Yep. There's actually about 5 million red blood cells in each cubic millimetre of blood. So that makes about 10 million red blood cells. That's 1 followed by 13 zeros in every one of us. Probably less in me because I'm quite small.
The most common chemical element on the Earth is hydrogen. Is that fact or fiction?
That's fiction.
He's right again, 2 out of 2. Hydrogen is the most common element in the universe, and it's about 75% of all the matter in the universe. But actually, Earth's most abundant element is oxygen, which accounts for about 46% of the mass of the Earth. Well done.
Okay.
Thank you very much, Dave.
Thanks.
Great to have you on the show.
Okay, cheers, bye.
Got an email here from Andreas. He's in Sweden, and he says, I've got a question about meat. How come different types of meat get different colours when they're cooked? Beef, for instance, turns dark brown, pork goes light brown, and chicken turns white. Most fish is also white, except for salmon and some other red fish. What makes the difference in the colour? Well, I was looking into this because I was pretty intrigued. And the answer, Andreas, is that it's all down to a chemical called myoglobin. Myoglobin's a bit like haemoglobin, the red-coloured stuff that contains iron that ferries oxygen around the bloodstream, except myoglobin is locked up in muscle, and meat is muscle. Now, some meat, which is red meat, contains a lot more of this myoglobin than white meat. And the reason is those muscles that tend to be red tend to be the muscles that are most often active in an animal. So if they're the muscle of the, say, legs when you're standing up all the time, that tends to be redder and have more of this myoglobin because it's a sign that the muscle has exercised or been tuned up for long-term activity. Muscles that you don't use very often are what's called fast-twitch muscles, and those ones tend to have very low blood supply. They tend to have very little of this myoglobin, and they're very white as a consequence. So chicken breast, for instance, and chicken wings, the chickens don't run around, they flap their wings, but they don't fly, and as a result, those muscles don't get a huge amount of use, and therefore they're white muscle. When you turn to fish, salmon have this red colour because most of the time we buy our salmon off the supermarket shelves and it's farmed salmon, and to keep the meat looking a nice healthy pink colour, actually the fish get fed something which makes their meat go red, and it's the same stuff that they would get if they were getting it in the wild, and that's something called astaxanthin. Astaxanthin is quite hard to say because it's ASTAXANTHIN, astaxanthin. And you get this in the environment from yeast and from algae, things that photosynthesize. And they make this chemical. It's a bit like the stuff you find in carrots that makes carrots orange. It's an antioxidant. It gets into shrimps and krill and things, and when the salmon eat those, they get it into their body, and they then put it into their tissues, which is why they go red. Now, that's how they do it naturally. We add that to them when we farm them, because people won't buy salmon that's a pale colour. It's also the same reason that flamingos have pink feathers, but I wouldn't eat the feathers of a flamingo for obvious reasons.
I think you'd be hard-pressed to find flamingo, even in Waitrose. Anyway, this week on our Kitchen Science, it's time for Kitchen Science. Ben Valsler is in King Edward VI's Grammar School in Chelmsford to find out how we can make a weather system in a bottle.
Hello, welcome to Kitchen Science. This week we're in King Edward's Grammar School in Chelmsford, and I'm, of course, with Dave Ansell.
Hi there.
And I'm also with my wonderful helpers, Henry.
Hello.
And Bryn.
Hi.
Now, Dave told me when I was on my way here that he's going to make a weather system in a bottle. So, Dave, what are we doing?
Well, today what you're going to need is an empty lemonade bottle, preferably a 2-litre one, those are best, a match, and a little bit of water.
So a little bit of water, an empty 2-litre plastic bottle, and a match. Now, is this safe for people to do at home?
As long as you've got an adult to use the matches, it's perfectly safe.
All right, then. Well, take us through it, Dave.
Well, first of all, Henry, if you'd like to get the bottle and put a little tiny bit of water in the bottle, maybe only half a centimetre. So Henry's putting a little bit of water into the bottle from the tap. So Henry's only put about half a centimetre of water in the bottom of the bottle, which will be plenty.
So it's really just like rinsing the bottle through and leaving a bit in?
Yeah, that's right. And now if you'd like to put the lid on and just gently swirl the water round the bottle to try and get rid of too many drops on the sides and keep it nice and clean.
How's your bottle looking, Henry?
Not a lot of drips on the side. Tiny bit of water.
OK then, Dave, so we've got a piddling amount of water in the bottom of a bottle. What's next?
Now, Henry, can you open the bottle? And I want Bryn to light a match. Just let it burn a little bit, so as you've got a reasonable amount of the match burning. If you point it downwards, it helps.
Again, you should be careful with matches at home.
With the bottle on its side, just to let some of the smoke go into the bottle. OK, now blow it out and put it into the bottle.
So, Bryn, what's happened in the bottle now?
Well, it's steamed up because of the heat of the match, but nothing else much has happened.
OK then, Dave, so we've got a bit of smoke in the bottle, we've got a little bit of water, and that's it. So I still don't see a weather system here.
OK, so now, Henry, if you put the lid on the bottle, now what I'm going to want you to do when we come back again is I want you to squeeze the bottle as hard as you can for about 5 or 6 seconds, sort of swoosh the water around a bit in the bottom, hold it really tight as hard as you can, and then let go, and see if you can see any change.
OK, folks, so get yourself an empty 2-litre plastic bottle, put a little bit of water in the bottom, light a match, blow it out, put it in, screw up the top, squeeze it as hard as you can, swirl it around a bit, and then let go and let us know what happens. We'll see you later in the show.
Thanks, Ben. And you will not fail to be impressed if you have a go. So the first person who can call in and correctly tell us what is going to happen when you do that, you're going to win a copy of Naked Science, which is my book, and I'll even sign it for you, which means it trebles its price on eBay, so it goes from being worth about 3p to about, well, 9p.
I said, I'll give you 5p for it. Yeah, and if you give us an extra £1, I'll sign it too. Anyway, we've been asking on the teaser what percentage is oxygen at the top of Everest. We've had a few answers in. Helen from Sheringham, not quite there. Bob in Ely, definitely right. Sue in Peterborough, not there. Mark in Chelmsford, not quite there. We've also had Fred and Scott, who unfortunately their guess on the teaser was wrong, but they've had something to say about the Hindenburg. So they said on the subject of hydrogen, the Hindenburg went up mostly because the skin was coated in aluminium and iron oxide, and this was, they made the fabric, coated the fabric with. And the small problem with this is that it burns really, really hot. It's called thermite, so obviously a load of hydrogen, something that burns really hot.
Yeah, sure. The skin they used that, the Nazis liked that because it gave it that nice silvery colour, and they wanted something that looked good against a swastika, and it's absolutely true. And yes, unfortunately they combined two of the most explosive combinations in the known universe in one airship and a thunderstorm, and so people wonder whether some static electricity from the tower that the Hindenburg was moored to could have been responsible for detonating it.
Laying the facts bare, the Naked Scientists.
Now, if you think our air today's polluted, spare a thought for those who lived in 1783 in Iceland, because there was a massive volcanic eruption, and that was the biggest atmospheric pollution event in history. Professor John Grattan's on the line from the University of Wales in Aberystwyth. Hello, John.
Hello.
So if this were industry, the government would have shut it down on health and safety grounds, this volcano?
Absolutely. It emitted about 17 times more sulphur than all of Europe today put together.
So tell us about the events that led up to this eruption and how it got documented and what the consequences were.
Well, it all began in early June 1783, really, in Iceland, really a very remote place at that time. And a very astute pastor called John Steingrimsson started to notice a dark cloud building to the north, and that was followed by sort of what he described as iron filings falling to the earth and burying the plants, etc. And then that was quickly followed by the smell of sulphur, and then within a day or two, the animals started to die and people started to die, and within a few days, the livestock had gone. At the end of the event, something like 3/4 of all Iceland's livestock, sheep, cattle, horses, had all died, and about 1/4 of Iceland's population. So it was bad in Iceland.
So what was the reason that those people succumbed and their animals too?
Well, there's several causes. The first one, as far as the animals were concerned, was that the eruption threw out fluorine, which landed on the vegetation, and the animals then ate it, and that released the fluorine into their bodies. It was a poison, and essentially their stomachs were blocked up with ash, so they couldn't ruminate. There was poison. This fluorine was in their body. That triggered uncontrolled bone growth. So you had the sheep, for instance, they would have their teeth would be growing uncontrollably, so they looked like fangs, and they were digging into the jaw above or below, so they couldn't chew anyway, and they'd get the joints of their bones would have sort of spikes growing out so they couldn't walk, and it was sort of very apocalyptic vision. And the people at the time in Iceland just saw it as the end of the world. This was the judgment of God on the sinful nation.
Is it a one-off, this kind of thing happening, or have there been lots of examples of volcanoes having this kind of catastrophic effect on populations before?
Well, I think there was an eruption on a slightly bigger scale in the 10th century, an eruption called Eldgjá, which was even bigger. And probably there's an eruption like this every 500 years or so in Iceland on this scale. But small eruptions in Iceland still release fluorine, and they do kill the livestock. As recently as 2000, the eruption of Hekla, the livestock in Iceland was being killed. But it's not just the impact in Iceland that's a problem. The Laki fissure emitted hundreds of millions of tons of sulphur into the atmosphere, and it was transported around the world, and a lot of it was transported to Europe, where it also had terrible impacts.
So if you add up how much comes out of one volcano, how does it compare with, say, mankind's activities? Because I've got an email here from Eric Taylor to a Latin who is in the USA, and Eric wants to know, how do volcanoes compare, say, up against cars, houses, industry in terms of their emissions?
You put me on the spot then, and that figure's just slipped out of my head, I'm afraid. But I can tell you, for instance, that Mount Etna, in a typical year, emits as much sulphur as all of France's industry. So it is a significant contribution. But you have to remember that the planet's ecosystem has evolved with volcanoes doing this, and the problem with man's emissions is that they're extra to this, and they often have concentrated local impacts in cities, etc., on forests which aren't expecting to receive a contribution of sulphur dioxide. Where a volcano's emitting sulphur, then the ecologies around it have grown and adapted to tolerate that.
If you look further afield than just the local environment, though, because you said these gases get spread right the way around the world, what can we say happens to the Earth's atmosphere and the environment and the climate as a consequence of volcanoes?
Well, typically, the gases get from a low-intensity volcanic eruption. The gases get emitted into the troposphere, and they're diluted by atmospheric processes. They're rained out as very dilute acid rain, and there's really no significant impact from them. But where we have large-scale eruptions, which are less common, say a 1 in 500-year eruptive event, for instance, then we're dealing with hundreds of millions of tons of sulphur being emitted in a relatively short period of time. And these then can be concentrated by atmospheric processes, and these can have a really severe impact. In 1783, when the Laki fissure eruption was taking place, there was a sulphurous dry fog was formed all over Europe, and people were describing how their crops were being killed, the leaves were falling off trees. People were complaining of the smell of sulphur, and they were coughing, and then the people were dying in great numbers. We think that in the summer of 1783, something like 20,000 people died in England and alone as a result of the environmental manipulation of this. So we've got two things going on. We've got the normal background, typical year-on-year eruptive activity, and then we've got these significant, once in 500-year events that do significantly stress the environment.
We've had similar things with the London smogs in the 50s, though, haven't we? I mean, we know that atmospheric pollution's bad for you.
We do, and certainly that certainly was the case in the 1950s. And indeed, when I was beginning to investigate the Laki fissure, I turned to these smog events to try and get an understanding of what may happen when you get significant concentrations of sulphur on the ground. And certainly, when you're dealing with an event like the Laki fissure, where it erupted for 8 months. I mean, people don't realise this. They have this idea that volcanoes are, it's a sort of few days where it erupts into the atmosphere. It's all very spectacular, then it dies down. The Laki fissure erupted for 8 months. And throughout that period of time, it's throwing material into the atmosphere. And so there's a long-term environmental stress from something like this. And so in our world today, if something like this was to happen, we could imagine a scenario where we have atmospheric pollution in London or Birmingham or any significant conurbation, and then one morning, courtesy of an Icelandic volcano, another 2 million tons of sulphur are delivered, and that's obviously going to push the environmental thresholds significantly, and then I think we could expect to see significant health impacts and mortality crises.
So you could actually say, because this thing blows up in Iceland, you would be able to trace a health effect in the UK, in France, and further afield, perhaps even Russia and Japan even.
Yeah, absolutely. We've traced this day by day from the moment the eruption began all the way through to 1784 when the eruption ended, and we've got a day by day history of the eruption and people's health, and we can see the arrival of the smog, the destruction of crops and plants, and then people are dying, and people begin to die in great numbers in August and September and October 1783. And the people writing at the time, and the people at the time were really amazed by this. You know, this sulphurous smog, and you couldn't see across the valley. They were amazed by this, and they were very clearly linking the arrival of the fog with the deaths of people. There were some French priests who talked about when the fog arrived, a third of the men in my parish were swept to their tombs. And people were really scared. There's one letter which tells of the people of one parish being so afraid of this fog. They obviously thought the end of the world was here and that the gates of hell had opened and the devil was walking the earth. And they dragged the priest out of his house and made him put on his vestments and perform a service of exorcism on it. And so we've got all this happening in the 18th century when really there's little industrial pollution going on. If an event like this was to happen in the future where we have significant industrial pollution or pollution in cities because of car and industry now, then we're dealing with an event where the thresholds for human health impacts are much closer.
I think we should tell that to the people who are coordinating the Beijing Olympics next year, because Beijing is said to have air which is unfit for humans to breathe on about 212 days of the year. But John, thank you very much for joining us. That's John Grattan from the University of Wales, Aberystwyth.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Now, climate change and the human contribution to the greenhouse effect has been a hot topic recently, and people are gradually becoming more aware of the dangers of greenhouse gases. But not many of us suspect that old H2O could be contributing much to the problem. Well, to find out more, Azzy Kateri went to the Department of Chemistry at Cambridge University to speak to Professor Rod Jones.
Just about everybody knows that CO2 is the most important greenhouse forcing gas. What they don't know is that water vapour in the atmosphere is actually about twice as effective as CO2 as a greenhouse warming gas. CO2 is put into the atmosphere by natural and man's activities. Water, on the other hand, evaporates from the surface, and its atmospheric concentration is then simply determined by the temperature of the atmosphere. And so as we put more CO2 and other greenhouse gases into the atmosphere, we force the temperature to rise, and therefore the atmosphere can hold more water. And the additional water leads to additional warming, which is an amplification factor or a feedback effect on the original forcing.
So the more greenhouse gases like CO2 we put in the atmosphere, the warmer the atmosphere gets, and the more water we evaporate, which then goes back into the atmosphere, which then warms it all up again.
Which warms it further, yes.
What happens as the sun's radiation comes into the atmosphere, and how does it interact with these water molecules?
Basically, the sun's radiation warms the surface, and the Earth's surface emits infrared radiation, which is at much longer wavelengths than the visible radiation that we can see, and it's that long wavelength radiation which is trapped by the water molecules in just the same way as that it's trapped by CO2 and by other greenhouse forcing gases. Now, the work that we're doing here is part of the water vapour problem, because water vapour is a very interesting molecule in that it doesn't just absorb as an individual molecule, but it can cluster together. Ultimately, it clusters together to form clouds, which have a huge impact on the radiative properties of the atmosphere. But we're looking at the first stages of that, where two water vapour molecules come together to form a dimer. And the point about the dimer, well, there's 2 points. One is that the absorption features of the dimer are very different from the absorption features of the water molecule on its own. And the second point is that as water increases in the atmosphere, the concentration of the water dimer is expected to increase as the water vapour squared.
How does the water dimer differ to the actual water monomer in its absorption effects?
The absorption of the dimer has the potential of being stronger per molecule than of the monomer. And so the purpose of the study that we're doing at the moment is to try and measure the absorption properties of the water vapour dimer so that we can then put those ultimately into the climate models which are going to predict future changes. The work we do is in a laser laboratory where one of my PhD students, Alex Shillings, has been working for a couple of years. I'm just going to have to go through the laser interlock door. Hopefully we can find Alex.
Hello, Alex.
Hello. I'm Alex Shillings. I'm a PhD student working on the broadband cavity ring down experiment, and we're looking for the water dimer absorption. This grey box you see here, this is a YAG laser producing green laser light. This green light is then injected into the blue box you see over here, which is a dye laser. So we put green light in and we get red laser light out.
So what happens then to the light that comes out of the dye laser?
It comes around those turning mirrors and is injected into the cavity. Once inside, the light bounces back and forth many, many times between the mirrors. We can get an effective path of the light of 30 or 40 kilometres, even though the dimensions of the experiment is only around about 2 metres long.
That's effectively reproducing what happens to the light in the atmosphere.
Absolutely right. That's one of the beauties of why this experiment is so appropriate for measuring species that could be important for absorbing radiation in the atmosphere, because we've got paths that are commensurate with, or indeed even exceed, paths of sunlight through the atmosphere.
So you've put whatever you want to measure effectively in the tube, and in this case it's water vapour, isn't it?
Yeah, that's correct. The actual thing that we measure is the time dependence of the light leaking out of this cavity, so how quickly it decays away. And we actually measure the difference between a cavity with water vapour in or an empty cavity filled with just air. And the difference between the two loss rates gives us a direct measure of how much radiation whatever's in the cavity is absorbing.
So effectively you're comparing your cavity with and without the species that you want to measure, and then the difference between the with and without tell you how much your species actually absorbed.
That's correct, yeah. So the water dimer is in actual fact two water monomer molecules that are stuck together by a hydrogen bond, which alters slightly the bond between the hydrogen and the oxygen in one of the water molecules. And because the hydrogen-oxygen bond is altered, it leads to a new absorption feature, which is the dimer absorption feature that we're looking for.
It's all very interesting that you can pick up these specific vibrations from water dimer, which, as Rod was telling me, is very important in the greenhouse effect. But are you working in collaboration with some atmospheric modelers, for example, to then put your findings into ways of understanding the greenhouse effect?
It's been a bit of an embarrassment for climate science that since the greenhouse effect was discovered, there's always been a disagreement between the amount of radiation that we measure the atmosphere absorbs and the amount of radiation that we predict the atmosphere should absorb from our knowledge of the composition of the atmosphere. Hopefully our measurements should be able to bridge that gap to some extent. And so once we've got a better understanding of the atmospheric system, we will certainly be better equipped to deal with the climate change problems that I think we're almost bound to be facing into the next century.
Our own Azzy Katiri talking with Cambridge University's Rod Jones and Rod Jones's PhD student Alex Shillings. Now, it's a very great pleasure to welcome to the studio from the British Antarctic Survey the guy who was one of the team who discovered the hole in the ozone layer in the mid-80s, and that's Jonathan Shanklin. Hello, Jonathan.
Good evening.
Thank you for coming to talk to us. So, actually, first of all, what is the ozone layer? Where is it?
OK, the ozone layer is high up in the atmosphere from about 10 to maybe 30 kilometres. And if you brought all the ozone in that layer down to the surface, we'd have just 3 millimetres of pure ozone gas. But that 3 millimetres is actually spread through maybe 20 kilometres of atmosphere. So even in the ozone layer, there's not much ozone.
So it's very thin, isn't it?
It is very thin. And the worry that we have for the Antarctic is that during the Antarctic spring, we have a hole in the ozone layer.
How did you actually discover that hole was there? What were you doing at the time that led you to make that finding?
We were actually making routine measurements of ozone. They started in the International Geophysical Year, 1957-58, and we'd been making them ever since. And really, the discovery was looking not to show that there was anything wrong with the ozone layer. We were trying to show that it was OK and that spray cans weren't destroying it, Concorde wasn't destroying it. And we spotted that during the Antarctic spring, ozone levels were dropping. And we followed that up, found that it was a systematic change, so that it was different each year, getting lower and lower. And then that was published in Nature, and the Americans went back to their satellite data and said, oh, whoops, yes, you're right, we missed it.
Why spring? Because you've mentioned that twice. You said every spring this is happening. What's the significance of the season?
The significance of spring is really why it's over Antarctica, and it's to do with the temperature high in the atmosphere. Once you get up to maybe 14 to 20 kilometres, temperatures get below minus 80 Celsius. And at that sort of temperature, you get clouds actually forming in the ozone layer. Now, chemical reactions can go on the surface of those clouds that convert the chlorine and indeed bromine from halons into an active form, which is basically chlorine monoxide or bromine monoxide. And then when the sun comes back in the Antarctic spring, you get very efficient catalytic cycles that convert ozone back into oxygen. So oxygen has 2 atoms of oxygen, ozone has 3 atoms, and we get about 1% a day being converted back to oxygen.
So what's the significance of the spray cans and things like that? How does that actually contribute?
Right,
and also, why is it just Antarctica? Why not the North Pole?
The spray cans used to be powered by chlorofluorocarbon as a propellant, and it was also found in upholstery foams, in plastic cartons, and a whole host of exciting uses. And they were mostly released in the Northern Hemisphere, but the process of diffusion means that these get well mixed throughout the atmosphere. Roughly speaking, the concentration of CFCs at the South Pole and the North Pole are exactly the same, but what is different is the temperature. Over the Antarctic, it's every winter cold enough to form these stratospheric clouds high in the atmosphere. But for the Arctic, it's only exceptionally cold winters just due to the circulation in the atmosphere. By and large, the Northern Hemisphere circulation is more complex, the atmosphere is better mixed, it's about 10 degrees warmer, so these clouds are quite rare. But they have been seen over Cambridge.
So why doesn't the ozone from elsewhere in the atmosphere just sort of flow into Antarctica and replace the deficit, the hole?
Essentially it can't. During the Antarctic winter, you get a very strong circumpolar circulation called the polar vortex, and that effectively acts as a barrier. It stops the air mixing from outside the Antarctic into the Antarctic. And so what happens is during the spring you get a build-up of ozone-rich air around the Antarctic. In the middle you get very low levels of ozone, and that's the ozone hole.
I'd just like to backtrack a bit and ask, why is the ozone layer so important? Does it really matter if it's vanished? Can't we just, take the ozone from down at street level and shove it back up there?
It does matter if it disappears, and what happens is that more ultraviolet light from the sun can get through to the surface when there's less ozone. And this UV light can trigger skin cancers, cataracts, genetic damage in microorganisms. So it's not very good for us to have too much UV. And, for example, when we have the ozone hole in the Antarctic, you can get burnt in 5 minutes if you don't put on factor 30 sunblock.
Wow. And how is it actually linked into global warming, which is something we're becoming increasingly aware of?
It's quite a complex thing. The ozone hole is actually completely separate in many ways from global warming, but global warming actually makes the ozone hole worse. And that's because the greenhouse gases act a bit like a blanket. The surface of the Earth is heating up, but in the ozone layer it's getting colder. And the fact that it's getting colder means that more of those clouds can form, more ozone destruction, gets colder still, and it's a positive feedback cycle.
That doesn't sound good.
Have the mechanisms we've put in place to try to limit the use of the agents, the CFCs we think are responsible, actually worked? Is the hole shrinking?
There's a big international treaty called the Montreal Protocol, and all bar one of the world's countries actually signed up to the basic thing. So that's really good news, very effective. And the amounts of these ozone-damaging chemicals in the atmosphere are actually going down. So we're definitely getting there with this one. But it is a symptom and not a thing in itself. And unless we tackle the basic level of what's causing many of these environmental problems, things can only get worse.
And just to finish off, Jonathan, just to sort of crystallise this in people's minds, how big is that hole over Antarctica?
The Antarctic is 50 times the size of the UK. The ozone hole is bigger than that. Not by much, but it gives you a bit of an idea of the scale of the thing.
So 50 times our own nation. It's quite a sobering thought, isn't it?
It is, and something that we created off our own bat.
In actually quite a short space of time.
As little as 10 years. And it shows you how fragile our atmosphere is and how much care we need to take in case something similar happens in the future.
Thank you, Jonathan. So Naked Scientists talking there with Jonathan Shanklin, who is from the British Antarctic Survey, one of the scientists who discovered the hole in the ozone layer. Now, talking of atmospheres and things, we asked you this week to see if you could create your own atmospheric system in a bottle, and what we asked you to do is put a little bit of water in a Coke bottle, light a match, drop it in, squeeze the bottle really, really hard and let it go. Andrew reckons he knows the answer. He's in Norwich. Andrew?
Well, I better explain. I've actually done this one, so it worked out in my head. I think what's happening is you introduce a very small amount of water so that it's not oversaturated. You send in the whiff of smoke, which provides nucleation centers. When you squeeze the bottle and then suddenly let go, you're causing a sudden drop in pressure, which should, I think, reduce the dew point and mean that water which was sort of basically in gaseous form should suddenly condense. So you should get a sudden appearance of fog.
OK, that's his prediction. Thank you very much, Andrew. Great bit of science there. Well, let's head back to King Edward VI Grammar School, where Dave and Ben are there, and they're actually going to do the experiment and find out if he's right. Hi, Ben.
Hello, welcome back to Kitchen Science. I hope you've all got a bottle ready. You need to put a small amount of water in the bottom, then you light a match, blow it out, and make sure some of the smoke goes in the bottle, seal the bottle up, squeeze it really tight while swirling that water around, and then you let go. And now Dave is going to show us what happens.
OK, I think the smoke will probably run out in the last half hour, so I want Bryn to light the match again. Let it just get burning, blow it out, and put it in the bottle. OK, now, Henry, if you'd like to put the lid on. Now, I want you to squeeze it as hard as you can. And just swoosh the water, not all the way out the bottle, just around the bottom. Bit of a swirl, a bit harder than that. You don't want to get it all the way out the bottle, but most of the way out. Really squeeze while you're doing it as hard as you possibly can. Really, really hard. Make a wonderful face there, Henry. Really squeeze for as hard as you can.
We're trying to put as much pressure on this bottle as we possibly can.
So now, Henry, how clear is the air inside there at the moment?
Quite clear.
OK, so 1, 2, 3, we're going to release on 3. 1, 2, 3.
Now, what's the air look like in there?
A bit misty.
So it's gone cloudy inside the bottle. Is that what's supposed to happen?
Yes, we've made a cloud inside the bottle.
So how did that happen?
OK, so we've done two things. We've put some smoke in there and we've squashed it. When you compress a gas, it gets a bit hotter. I don't know if any of you have used a bicycle pump. When you pump a bicycle pump really hard into a bicycle tyre, have you ever noticed anything happening to the temperature?
Well, the temperature goes really high and it's quite hot.
That's because when you compress a gas, it gets hotter. And when a gas is hotter, it can hold more water.
So we compress this gas just by crushing the bottle as hard as we could?
Yeah, which means water can evaporate and you get more water in the gas. OK? Then when you release it all of a sudden, the opposite thing happens, it gets colder. This is a bit like if you've ever used a spray can, the gas expands, which means the spray can sometimes feels quite cold. So the gas suddenly gets colder, which means it can't hold as much water, so that water wants to stop being a vapour and turn into a liquid again.
So this is a bit like what happens in the atmosphere when there's hot air that's got lots of water vapour in it, and when that gets cool, the water condenses out, and that's how we get clouds in our sky. But why put smoke in a bottle?
Well, the problem is that actually forming a droplet of water is quite difficult. It needs something to start on. If we didn't put any smoke in there, there'd be nothing for it to start on inside the bottle, and it would probably just condense and make a little bit of dew. With lots of little smoke particles, it gives it somewhere to start inside the bottle, so you get little drops of water in the air, and it makes a cloud.
What do you think of that then, boys? Ever made a cloud in a bottle before?
No, I think it was quite cool. I've never done that before.
Well, that's about all we have time for in Kitchen Science this week. I do hope you squeezed your bottles at home and made yourself a pretty little cloud in a bottle. Thank you very much to everyone at Kegs, but it's now goodbye from Dave.
Goodbye.
It's goodbye from me, and it's goodbye from the boys.
Goodbye.
Cloud in a bottle, nearly as good as having a genie in the bottle. Well done, Andrew. That means you've won yourself a book.
Oh, have I? Yeah. Oh, fabulous.
So if you want to have a go at Kitchen Science next week, tune in Naked Scientists. Now, very quick question, if you can do this in a couple of seconds for us, Jonathan. Tony is in Bury St Edmunds and wants to know, is the total amount of water around the world increasing as we burn more fuel?
So yes, but, and the answer was just given, in fact, because the Earth is getting a bit hotter, or the atmosphere is getting hotter, it can hold more water vapour, so yes, the amount's going up.
Thank you, Kat.
Brilliant. And we have an answer on our teaser. We asked you what percentage of the oxygen is there at the top of Everest. And the answer is it's the same as it is here. It's just that there's less air pressure. So there's, lower pressure of gas, but actually the percentages are the same. And we have the winner, who is Alana Ray.
Thank you, Kat, for breezing in with that answer. Right, well, that's pretty much all we've got time for on this week's edition of The Naked Scientist. Next time, we'll be jetting off from planet Earth in search of habitable planets elsewhere in the universe, because Maggie Turnbull from the Space Telescope Science Institute will be joining us to talk about finding habitable planets elsewhere in space and how she's doing that. She's narrowed the number of planets she thinks have habitable zones down to a very small number, and she'll be telling us where they are, and what the criteria are, and how she finds them. We'll also be joined by Cambridge University's Carolyn Crawford, and she's going to be talking about everything else to do with space science. So if you have any questions on space science, astrobiology, tracking down habitable planets in other solar systems, then send them to me now, chris@nakedscientists.com, and we'll endeavour to squeeze them into next week's programme. Well, that's pretty much it for this week. I've got to say a very big thank you to Jonathan Shanklin from the British Antarctic Survey, to John Grattan from the University of Aberystwyth, Wales, Rod Jones and Alex Shillings from Cambridge University, and of course to our production team, Ben Valsler, Azzy Katiri and Petro Minch. And on the Naked Scientist website, do check out our forum, nakedscientist.com/forum, where there's a thriving hubbub of scientific activity just waiting to be discovered. We'd love your input there. Hopefully we'll see you. Until next time, goodbye.